Hello everyone. My name is Atreya Vedantam. I am I am doing Bachelor of Technology in Electrical Engineering at IIT Madras. My rank in JEE Mains was 221. My rank in JEE Advanced was 315. Today, we'll be talking a bit about electrostatic potential and capacitance. This chapter. In brief, we will understand all the concepts that are associated with electric potential and capacitance. And towards the end of the chapter, we'll also be solving a couple of problems to get a feel for how problems appear, how we may tackle them, what methods can we employ to efficiently solve such problems. So we'll be looking at all of these. So let's get started. So briefly, let's look at all the concepts. So the moment we see this chapter title, we have to analyze what the chapter name means. So what is electrostatic? So let's break this word down. So electro. So clearly this has something to do with electric charges. So that is the word. Static. It's a very important word that a lot of people fail to understand that this is a really, really important word. And a lot of people actually leave this word out, and a lot of concepts people get wrong because they don't understand the importance of this word. Static meaning stationary. So essentially this field, this electrostatics, is a field which has to do with stationary charges or the charges moving relatively slowly so that the approximation of them being stationary is good enough for us. This is what it means. Another thing I would like to clarify is, what do you mean by stationary charge? What charge is stationary? Does that mean no charge is moving? Or are all charges fixed forever like this? No, that is not the case. The case is the charge which is used to create the effects are stationary. That is, say a charge is producing an electric field. We will soon see what an electric field means. So this charge which is producing this field and causing other charges to move around, this charge is stationary. That's what it means. So it doesn't mean that all charges are stationary. It means that the source charges are stationary. Okay? Because if the source charges start moving, we get a lot of weird effects. And this is the collective study of these effects is called electromagnetism. So we'll soon look into how that comes around. And that study is called electrodynamics. However, right now we are going to restrict ourselves to electrostatics because it's far simpler to study. So there are a few times where I'll be mentioning concept, and I specifically mentioned that it is only valid for electrostatics. Okay. So in those cases, it's important to keep in mind that they do not apply for electrodynamics situations where source charges are moving around. Okay. Next, we see the word potential. So what does potential mean? Well, in colloquial English, potential is a measure of how good or smart or how much you can achieve or how much you can be, right? That's what people use potential. People associate the word potential with such kind of things. And here it means something similar. It is the amount that the charge can do things to the surroundings. We'll make it more precise later on. But to get a feel for it, it means the amount that the charge can exert on its surroundings. What can it exert exactly? We will look at things related called work, its ability to pass on energy. All of these terms are related with potential. So that is related to the charge's potential or the ability to give out energy, do work, and so on. Now, finally, we come to capacitance. Now, capacity should be a relatively a regular word that people use. Capacity means how much you can hold, right? And in this case, capacitance is a measure of how much charge a certain device can hold. And we look into exactly what kind of device that is later on. But that is what this means. So in this chapter, these are all the things that we're going to study. First, electric charges. Second, they are stationary or approximately stationary. And they have potential. That means they can exert influence on other charges. They can make other charges move around. They can make other charges interact with each other. And we look at objects called capacitors. We'll see and exactly how they hold charges and how we can use those devices to make our life better. Okay. So, well, so I think we have seen what what potential energy is in class 11. It is the ability of an object to do work, right? So if you have a lot of potential energy, then you can give out that energy to other objects. That is what having potential energy means. That means you can do work on a lot of things. So we see in a simplest case, like when you have the earth and a ball, if the ball goes up, it gains potential energy, more potential energy. And this ball here at a lower level has less potential energy. Why? That's because now that the ball is very high, it can now be made to fall down, and a lot of kinetic energy can be extracted from it because it's falling down at a very high speed. Whereas a low ball will only fall at a very small speed, so there's a very less amount of energy that you can extract from it. So that is the definition. That's what means to that's what people mean when a body has more potential energy. Now, what is potential? We'll look into this later. But let us move away from this mechanical analogy and get into electrostatics. So, we have discussed in the last few chapters that we define something called an electric field. So, an electric field is simply a object that we define in space that is caused by charges. We say that a charge produces something called a field in space. And even though we cannot see this field, we can feel its effects. So we can feel what it does to other charges. So classically, we used to think, classically, the model is to treat the influence of two charges as with each other. However, this model of having a field, that is, the positive charge will exert this field irrespective of whether there's another charge. It doesn't matter if the charge is there or not, this field will be there in space. Now, when this charge is put here or placed here, then the charge will experience a force according to the magnitude of the strength of the field at that point and the magnitude of the charge there. So the simple way we defined a field was the force or the electrostatic force on any charge Q is the magnitude of the charge times the electric field at that point. And very importantly, the direction of the force is the same as the direction of the field. So that is how we define a field. The definition of field follows basically as it is the force exerted per unit charge. Okay. So now we define what potential is. So coming to what potential is. So let's say we have a stationary source producing charge Q. Okay. Like it has a charge Q. It's a stationary charge. That's why it's static, remember? And it's producing some electric field in space. Now you are bringing this charge Q. So you are a person who's trying to bring the charge Q from the point R to the point P. Now you know this charge is positive and this charge is also positive. So these two charges are going to repel because like charges repel, right? So you see that the force is going to be away. So this plus Q is trying to push the small q away. But you are adamant. You don't want it to go that way. Instead, you are trying to push it to P. So what you are doing is you are exerting work. So you are doing work on Q against the electric field. Because the electric field is trying to push the charge away, whereas you are trying to push the charge in the other direction. So you are doing positive work. What does positive work mean? You are basically trying to increase the energy of this Q. Because the moment the Q is at point P, it has a greater tendency to move away. So more energy can be extracted from it. Therefore, you can think of its potential energy as more here. Just like we saw in the ball being higher, having more potential energy case, charges close to each other generate more potential energy because they can get pushed away more. Okay, so that is how we define the potential as. You see, this point has more potential, P, whereas whereas R has less potential. So how much potential did it gain? What is the change in the potential energy? Well, the change in potential energy is the same as the work that you did, right? That is what the work energy theorem says. Or in other words, the change in energy of this charge Q is basically the energy that you gave to the charge. And how did you give the charge? Through the work that you did. So this is what it means. But you know that this work, by definition, is R to P F external, as in you are the external force, dot dr. Right? This is what it means. And you know that you can change the integration limits with a negative sign at the cost of a negative sign. And this is what happens. So this is the work that is done against the electrostatic repulsive force. So this potential difference is the work done. So a very important. So now we come to a very important point. In electrostatics, please note this word statics very, very carefully. In electrostatics, the work done from R to P is independent of the path. In other words, these electrostatic fields are conservative. Conservative as in the work done on a closed loop due to their forces, conservative, is zero. That is, they don't generate, using this fact, you define something called a potential. So that is very important first. To discuss the very idea of what a potential is, right? You need to know that the fields associated there are all conservative. Potential, now you may just think of potential as a point in space. A point in space having a certain number. You can think of this point having the number +3. You'll see soon that the units of potential is volts. But right now we can ignore that. And some other point having, say, +7. So each point in space has a number. And this number is a measure of how much energy that point has. Or it's a measure of how much a charge can get affected if it's at that point. So now let us say that we have these numbers are decided by the charge distribution. So there could be a bunch of negative and positive charges, and because of the contributions of all of this, each point in space has a number. Any point in space that you give me has a number, and a very important property is that every point has only one number at a given instant of time. At a given instant of time, if this is 7, it cannot also be 5. That is not allowed. If it has one potential, then that is what it is. Okay. And this property comes from the fact that these fields are all electrostatic. Okay. Soon we will see a case where this is not true. Okay. So let's say this potential is at this point is +7, right? Let us say that there's a charge of 3 coulombs that we are going to place. Okay. The potential energy of the charge is therefore +3 into +7, which is 21. 21 joules. Okay. That is it. So the potential at a point determines how much energy it has by multiplying it with the magnitude of the charge. If the charge are more, obviously it would have more potential energy. So in fact, this is an unfortunate naming thing. Potential and potential energy are very different. I said they're not very different, but they definitely differ significantly conceptually. This is potential. This is potential energy. Potential energy also takes into account how much charge you have at that point. Potential does not take into account how much charge is there at that point. It, of course, is affected by other charges. It's affected by source charges only. So that's an important concept to keep in mind. Okay, so this is what. So if the plus 3 coulomb were here, it would have 21 joules of energy. If the plus 3 coulomb were here, then it would have an energy of 9 joules, 3 into 3. So now you can automatically see that at this point, it has 21 joules, and at this point, it has 9 joules. 9 joules. And now you know that particles always move from a higher potential energy to a lower potential energy, right? Like when you release a ball from above, it comes down because it wants to decrease the potential energy so that it increases kinetic energy. And that's exactly what happens here as well. So if you leave this charge here, if you let go of the charge plus 3 here, it will run away to here. It will start running towards here. And here at this point, it will have some kinetic energy this way. As in, it will have some velocity this way, and it will have a positive kinetic energy. So that's exactly, you see the analogy. If you let go of a ball that's high, it's going to come down low. It's going to have a lot of velocity this way. Just like that, if you let go of a charge here, it's going to run off here, and it's going to have a high kinetic energy. It's the same thing, basically. Basically, in this case, the Earth is acting like a charge. You know that from gravitation, charges and masses, they have very similar laws, right? So the mass of the Earth is acting like a big charge, which is pulling the ball towards itself. Okay, so enough about this then. So hopefully that's clear. Another very important fact that I'd like to speak is this number plus 7 volts and this number plus 3 volts is decided by an arbitrary ground zero. Like this number is actually, you cannot determine in reality without determining an arbitrary 0 point. So this number could as well be 7 plus some alpha. In that case, this would become 3 plus alpha. So the difference should be the same, but you can arbitrarily add any constant to it and it would be perfectly fine. Because the definition of energy itself is basically involving with some reference, right? So that reference is usually negative infinity, but in some cases it will not be. Okay, so that's a thing to keep in mind. Like if you have infinite charge distributions, let's say an infinite plane, then the reference being a negative infinity is a bad idea because all your answers will result in infinities. In that case, you would like to only look at the change in potential from one point to another point. Only that would result in finite changes. Okay. So this is a very large chapter, so we're going to cover it in 2 sessions. So I don't want to rush and miss a few very important concepts. So here we are. So just like we've discussed, the change in potential energy is caused by the change in the potential. That's what we just saw, right? I just said that U is equal to Q times V. That is the potential energy is equal to the charge times the potential. But I have just discussed that everything is with respect to a reference. So this is a more accurate statement to make. So you can see here that Vp minus Vr, which is delta V, is equal to delta U by Q. So just like how force is Q times E, you have delta U is equal to Q times delta V. Now I think you may be able to see the similarities, right? Just like force and potential energy, you have electric fields and potentials. Okay. So here we have discussed this very important fact that in the case of electrostatic fields, the work done is path independent. So it doesn't matter what path you take from R to P. So as you can see, these are all very different paths, right? This path 1, path 2, path 3, path 4, path 5. But all of these paths will result in the same delta U, which is why you can ever define a delta V. I think you can sort of understand why potential is so sacred only in the case of conservative fields. Because if the work differed, if your delta U was different for each path, if this was the case, if delta U was different from path 1 and path 2, then maybe I could define an arbitrary different path and I would have a different potential energy. Then how can you define something called a delta V, right? The delta V would differ for every path. Then it would make it almost useless because this point P could have any number of potential. It could be plus 3, plus 4, plus 5 or whatever and so on. And there's no point in some point which has like infinite number of possible potentials. So it would make no sense to define something called a potential then in that case. So that's why only for electrostatic field, because it's conservative, all the delta U's are same. Because of that, you can equate all of these delta U's to the same Q times delta V. That's why you have the same delta V between 2 points. Okay. Now we come to sort of more rigorous individual examples. Let us say we had a point charge at the origin. Okay, we can define the origin anywhere we want. We can define it to be here also. The issue is that we will have something called a position vector. That is a vector to determine where the source charge is, and another vector to determine where the test charge is. That is a charge that is being affected by the source charge. And then we'd have something called the displacement vector between these 2 points, and we have to make the calculations much more complicated. So for this case, let's just assume that the source charge is at the origin. The test charge is at a vector r away from the origin. So let us say that let's say after a while the charges come to p prime. So let us say that's at a vector r prime. So I think because we want to determine the potential, and you know that potential energy can be calculated using the formula for work, right? You know that we can calculate potential energy like this, and we want to equate it to Q times delta V. We might as well make Q as 1 coulomb. We basically directly calculate delta V, right? So I hope that's fine. By the way, a very fun fact that I was telling you about that the unit of potential is voltage, right? Is volts. And a lot of us actually pronounce this wrong. This was actually told to me by my an electrical engineering faculty from IIT Madras. He said that the actual pronunciation of voltage was voltage. You have to press your lips. You have to press your teeth to your lower lip and say the, not voltage, like a lot of us do. Anyway, it's irrelevant but very interesting point. So yes. Anyway, so from Coulomb's law that this is the electrostatic force. So we can calculate the work done from r prime to r prime plus delta r prime, because we want to calculate the change in the potential energy, right? So that's what we are aiming to do. We are calculating what is the work done for the test charge to come from r prime to r prime plus delta r prime. So very simply put, let's do it on our own. You have a plus q, you have a plus small q. So let us say you are so remember that if you're going to push it from here to here, you have to do work against the electric field, which is equal to where I'll get more space. The electric field is equal to we'll just directly write the force. Force is equal to Q times, but small q is 1, right? By 4 pi epsilon naught r squared. This is the force r cap. Very important. Do not forget the direction. It's a good practice to always keep in mind that this is the r cap direction. So this is the force, right? And you are exerting another force, right? This is called external force. Now, what amount of force do you need to exert to bring it to here? Well, technically any force that is greater than the electrostatic repulsive force. Sorry. Any amount of force that you exert that is greater than the repulsive force is enough actually, because you are just going to push it, right? Then there's a positive acceleration and you're going to end up here. But unfortunately, when you end up here, you're also going to have a lot of kinetic energy. So that is some extra amount of energy that you put in. Whereas we would like to only find delta U, because we want to find out what is Q delta V, right? We want to find out potential. So what we do is we try to make this kinetic energy 0. So in order for that, we have to have our external force approximately equal to the repulsive force, only very slightly greater than, because we want to very gently push it, right? So at equilibrium, these both are actually equal in the limiting case. So it will take an infinite time for this charge to get here because it's an almost exact repulsive force. So this is the external force that you are applying. This is the charge repelling. So you are applying the same amount of force as a repelling charge. So it should technically stay there, but you're applying a very, very tiny amount of extra force. So that's going to bring it very, very slowly to this point. And now at this point, it has no kinetic energy because you have brought it very, very slowly. And therefore, you can calculate what the change in the potential energy is. So what is the work that you put in? Well, you are putting in Q by 4 pi epsilon naught R squared minus R cap because you are pushing it in the opposite direction. Dot dr. Dr is moving this way, right? So this is dr also minus R cap. Now minus R cap dot minus R cap is plus 1. So the dot goes away. And this is what you're integrating from. I told you that you need a reference, right? So generally the reference is at minus infinity. So you're bringing it from a very, very far point or plus infinity, doesn't matter. You're bringing it from some point and you're taking it to some distance at r away, right? At r away. So I'll put the dr here. And this is a very simple integral. And it basically sums up to Q by 4 pi epsilon naught r. So where this is the magnitude of r, just to be clear. So so this is the potential energy. This is work done per unit charge, right? Per unit charge. And therefore that is equal to the potential at that point. That is how we define the potential at that point. Okay. Yes. Oh, sorry, just to be clear, there's a negative sign here because the path is not r, it's not dr minus r cap. It's just dr, r cap. So there is a negative sign. That's why you get a positive potential. Okay. So that is how. So you see, the electric field varies as 1 over r squared. This is the most important fact, really. This is the most important conclusion that I want you guys to remember. The electric field, magnitude of the electric field varies as 1 over r squared. That is, it dips off very, very fast. So it's initially here, but after a while, it's very, very low. Whereas the potential, which is a scalar, remember, the potential is not a vector. In fact, if I am to sort of deviate very slightly and explain why some people might have thought of potential itself, the significance of thinking of such a thing is so that you don't have to deal with complicated vectors like the electric field. Vector operations are always very difficult. That is, they're very complicated, they're long and so on. But potentials are very simple because if you want to superpose, we have done the principle of superposition, right? The vector addition is much more complicated than simply a scalar addition. This is simply adding the two numbers. But here it's not simply adding, you need to take in the directions as well. Right? So yeah, so the point is vector addition is far harder. So we prefer to deal with potentials. So the reason potentials were even thought of is because they are scalars. So I want you guys to remember that. Now potentials varies with the distance as 1 over r. That is, it starts off lower, but as r increases, it does not dip, it does not fall off as fast as electric field. So that is a very important fact. These two are important observations. By the way, this is for electrostatic point charges. Later we will see that they're very for different charge distributions you'll get different variations with R, but this is for a point charge. So now you have different things like potential due to a dipole. So all of these are derivations really. So 1 second. Yeah. So here, so in the potential due to a dipole, we look at so a potential dipole. So let's look at what the word means. Dipole. A pole actually means a charge. Okay. The pole just means a charge. Di means two. So it really just means two charges. But the special property of a dipole is that one charge is positive and the other charge is negative with the exact same magnitude, and an idealized dipole is when these charges go to infinity, and let's say they have a distance, okay, and the distance between them is generally known as 2a, okay. I mean, the distance is actually d, but you just call it 2a for convenience. A should tend to 0. So this is an idealized dipole. Ideal dipole is when q is almost infinite and the distance is almost 0. So if you think about it, if q was some finite value, if q were 3 and a tend to 0, then you'd have a plus 3 coulomb and then a minus 3 coulomb at the same point, which would essentially be 0 coulombs. So it should not do anything, right? That's pretty boring. So what we physicists do is, as this happens, let us make a competing effect. So the competing effect is that they both tend to infinity. Now this is very interesting. Infinite charges surely should be very, very interesting. But then since there is an equal amount of negative infinity, that should sort of make it 0. But they're also not exactly at the same point. So you can't say that they exactly cancel out. So they should have some very interesting effects, right? That's exactly what we do in physics. Q tends to infinity and A tends to 0 in an ideal dipole. So, okay. So now coming here. So you have something called a dipole moment. Okay, it's a vector defined along, it points to the direction of the positive charge. So here you see plus Q. So it points towards that. It points away from the negative Q. It points upwards in this case. Usually the origin, we mark it equally symmetric with respect to plus Q and minus Q. That is why we in fact name the distance 2a, because we can say this distance is A and this distance is A. So yeah, and so now we try to find out what the field and what the potential is at some point P at a distance of R. And usually what we say is we'll find this thing very, very far away from where the magnitude of R is much, much, much greater than A. Because as you've seen, an idealized dipole is an A should tend to 0, right? But in reality, A is actually some finite quantity. So to simulate this effect, we try to measure all our things very, very far away. So the further away we do, the smaller A appears to be because of this approximation. So it's actually not a very complicated thing. We know that the potential due to a single point charge is 1 by 4 pi epsilon naught Q by R. So it's just a question of applying this multiple times. You see that they've applied it to one charge and then there's a second charge. This charge is a negative sign because it's a minus Q. And then use the cosine rule. I use the binomial approximation. See, this is the binomial approximation. 1 plus x to the power n is approximately 1 plus nx as long as x is very, very close to 0 and nx is not very large. It's very important actually. Nx should not be very large, but if x tends to 0, this is a valid approximation. So that's what they do here. In fact, the most popular case is 1 plus x power half, because you want to approximate 1 plus root x as 1 plus x by 2. Very simple approximation. So this is the formula that you get for dipole moment. So the potential is P dot R by 4 pi epsilon naught R squared. So now you can see, P dot R cap, my bad. So now you see that the potential actually falls off as 1 over R squared. Very interesting, right? And you may ask, okay, how does this dimensionally work out? But the reason it works out is because the units are all fine. The dipole moment, I have not defined what dipole moment is. I'm very sorry. I'll do that now. Dipole moment is defined as the magnitude of the charge, which is Q. You can see Q here, right? This magnitude times the distance between the two charges pointing towards the let's say the plus Q cap, okay, plus Q. So I should probably say P cap, okay. So that is the way the dipole moment vector is defined. Okay, it is basically charge times the distance. So now you can see why it's very interesting, right? If charge tends to infinity and distance tends to 0, you'll have an infinity times 0, which is indeterminate. It's not undefined, remember? Very careful. Okay, that's a mathematical thing, but I just like to point it out. Infinity times 0 is not undefined. It is simply indeterminate, because with different orders of infinity and different orders of zeros, the answer can be determined. So that is the thing. Okay, so yeah, and you can find out that this is the formula for the potential. And this is for trivial cases where, theta is equal to 0 and pi. Just put the dot. See, if you just say, if theta is equal to 0, then P dot R cap is simply just P. So you have 1 by 4 pi epsilon naught P by R squared. Whereas if theta is 180 degrees, then it is minus P, then it is minus. So that should be roughly straightforward. So anyway. And then a very important fact I want you guys to remember is that for pi by 2, it is 0. That should make sense, right? If you have a plus q and a minus q, at theta is equal to pi by 2, you are measuring the potential somewhere here, right? But even without thinking, it's fairly obvious, because the potential here is going to be some positive potential V, but here it is the same negative charge q. And because these two are symmetrical, they have the same distance. If this distance is L, this distance is also L. So whatever plus voltage this Q has offered, it's going to be exactly countered by this negative charge, because it is the same distance, the same magnitude of potential. So overall, it should become 0. Remember, what is the power? What you see the power of the potential? You can just add. If these are vectors, you couldn't do that. If this is a vector, then this would point this way, this would point this way, and the overall vector would point somewhere like that. That would not be 0. You see that? Whereas, lucky for us, potential is not a vector. It's just a scalar. So it's just a number. So whatever potential is caused due to this charge plus V, there's another potential caused minus V due to this charge, and you just say V minus V is 0. Simple algebra. That is the power of potential. Yeah. Another fact I should emphasize is potential and electric field due to a point charge are radial. That is, if you take a circle or a sphere, more accurately, around the charge Q, the potential value of the potential is same at all points of the sphere, and the value of the magnitude of the electric field is same at all points. The directions are obviously different. They're obviously radial, but radial symmetry is an important point to keep in mind. Okay, we will do potential due to a system of charges now. And lucky for us, I think we just discussed superposition in the case of potentials. It is simply the scalar addition. You just add all the numbers, 3 plus 4 minus 5 plus 6. That's it. There is no worrying about I cap, J cap, magnitudes, directions, Pythagoras theorem. All of that is not to be considered here. And that is the major advantage of doing this. So because every charge distribution can be broken down into multiple point charges, we just simply write this. So this is V1, this is V2, this is Vn, and you simply add all of it. Remember that the potential is point dependent. So when I say V total, I mean at a certain point. Okay, obviously this V total will be different for every point, because all of these R's are going to be different, right? The moment you take a different point, if this is a source, this is location 1, location 2. If the source could have multiple charges, all of those distances contribute to this potential at 1. And it's just a summation of all of them, right? But here, all these distances are very different, right? So this potential is going to be totally different. In a general case, obviously, if you argue to me saying, it could be the same and so on. Yeah, it could, but it need not necessarily. That's what I'm saying, right? So, okay, so the potential due to a uniformly charged shell is Q by 4 pi epsilon naught R, for R is greater than or equal to the radius of the shell. Okay, it's an important formula to keep in mind. Whereas inside the shell, it's simply constant. And that should make sense, because let's say you have a uniformly charged spherical shell like that. Okay, it's hollow. That's what a shell means. So it's all hollow inside. So outside it's going to project an electric field like this, right? Like the sun. I'm very bad at diagrams, but there you go. So when you're trying to bring a charge from all the way from infinity up to this point, you're doing work against the force, right? There's some force trying to stop you. And at every point, you're with all your hard work, you're trying to push forward, right? So all of your pushing, you've expended a lot of energy and you've given this plus Q a lot of energy here. So throughout this process, the potential should keep increasing because you're doing work against it. Whereas inside the uniform charged spherical shell, I'm sure all of you know that the electric field is zero. Now, because the electric field is zero, for you to bring this charge from here to the center, you don't need to apply any force at all because there's no force against you, right? You can just give it a gentle nudge and it's going to float all the way over there. Because of that, you are not putting any external work. Therefore, there is no extra change in potential energy. Therefore, there is no change in the potential of the point, which means whatever potential there is in the surface of the shell, it is the same potential everywhere inside. And what is that potential? Where replace R with capital R because at the radius, right? So you have this formula. I hope you understand. This is everywhere inside. So whenever you're asked to calculate the potential, it's important to calculate both inside and outside as two separate cases. Because they have different. So whenever you're asked to calculate potentials, you have to calculate always differently for different regions of electric fields, obviously. If you have the same electric field, obviously, then it's going to remain the same. Qualitatively, it's going to remain the same, right? The calculation. Whereas in a different region, if you have a different sort of electric field, in a different region, you have some other electric field, and in some other region, you have some other electric field, then for each of these cases, you have to calculate. You have to say case 1, case 2, case 3, and each of these regions will have a different way of the variation of the potential. So you need to take into account all of that. Okay, now we come to what are called equipotential surfaces. Well, what does this tell you? Well, potential is something that you've heard a lot of times in this lecture. But potential means, I hope you know what it means right now, right? It's Q by 4 pi epsilon naught R. Equi just means equal. That's it. It's not very complicated beyond that. It is just a surface. A surface doesn't it will be a sphere in this case. In this case, you can know that it is a surface where the potential is the same value. That's it. So if you have a plus Q here, at distance of 3 meters away, you know that the potential is Q by 4 pi epsilon naught into 3. And this value is the same everywhere, no matter where you take, right? All points on the circle or on the sphere, whatever in 3 dimensions, they're the same value of the potential. Therefore, they're called equipotential because it's the same potential. Okay, that's all it means. So all of these spheres are equipotential surfaces because all of them have their own potential at that point being the same. Obviously, these two don't have the same potential, and these two definitely don't have the same potentials. But whatever potential this has, maybe plus 3, is the plus 3 here, it's plus 3 here, and it's plus 3 here as well. Another important fact is, okay, we'll look at properties of equipotential surfaces soon enough. Okay, a few properties. Electric field lines or in electric fields are perpendicular to equipotentials. Okay, and I think we need to take some time to understand what is meant by in this statement. So look at an equipotential. Okay, say consider this charge. Okay, this charge, and you know that this diagram represents the electric fields, right? These arrows are the electric fields. Now, what does an electric field mean? We have discussed this already. If you have a charge Q, then if it is at that point and the field is pointing in this direction, then it's going to experience a force in this direction equal to Q times E at that point, right? So this electric field is trying to push the charge along that line. Now you know that we have discussed it also, that when two charges are close by, their potential is more, and over the course of time, as this Q is getting pushed away, and away, its potential energy is decreasing, and its kinetic energy is obviously increasing because it's gaining speed here, right? It's gaining speed. Okay, so you know that's happening, which means you know that points closer to this plus charge have more potential energy, and points further away from the plus charge have less potential energy, right? Technically, this statement is not correct because it depends on the sign of the charge that you're having there. If it's a negative charge, then the reverse is true. But for simplicity, or in other words, okay, I'll just say potential. Okay, potential energy is not the right term because if this charge happened to be in my negative 1 coulomb, then this is going to get attracted very badly, right? So that's a different case. But what I definitely mean is that the potential here is definitely much more than the potential here. So what's going to happen is the equipotential surfaces, which are circles in the case, or spheres, have decreasing potential as you go along the electric field. That is, when you're closer to the point charge, you have more potential, say +5. Okay, but you know that at this point it's going to be only some +3 because you know that along the electric field potential should decrease because the charge is getting pushed away, right? If the charge were at +5, it would prefer to go to +3 and give away the rest of the energy as kinetic energy. So, but because this is +3, this is +3, and this is +3, all of them are +3, and so on. So, if you take another equipotential surface somewhere over here, that would maybe have +1 as its voltage, as its potential. I mean, the reason is along the electric field, the potential energy of the positive test charge decreases, and therefore the potential of the equipotential surface should decrease. Okay, so that is one thing. Potentials decreases along equipotential surfaces. Okay, but what about this statement? Electric fields are perpendicular to equipotentials. Well, that is because what does it mean to have equipotentials? I think we have very briefly discussed what it means to have a difference in potential, right? If you have a potential of +10 and this potential is +5, then a positive charge would prefer to go from 10 to 5 because it wants to remove the potential energy and convert it to kinetic energy, right? So any charge would prefer to go from any positive charge would prefer to go from a higher potential energy to a higher potential to a lower potential. But what about another +10? What if I had another point of +10? Would it have any preference to go there? Absolutely not. Because, well, if it takes all the pain to go there, then it's going to end up having the same potential energy. So it's not going to have any kinetic energy. So what's the point? It's not dropping to a lower potential. That's why if you release a ball in the sky, it doesn't go sideways on its own. Because sideways, it has the same potential, right? If it has a potential of 3 joule, potential energy of 3 joules here, it's going to have a potential energy of 3 joules. Down, it's going to have a potential of energy of 1 joule. Above, it's going to have a potential energy of 5 joules. It will definitely not go up because it doesn't want to increase the potential energy. It definitely wants to come down because it wants to decrease the potential energy and convert it to kinetic energy. But it doesn't want to go sideways because it doesn't achieve anything by doing that. So, if 2 points have equal potentials, then the charges are not motivated to go there. Okay, so that's why when you leave a charge on the equipotential, if you leave a charge here, right, +Q, if you leave a charge here, it will not go here. In fact, it will only go here, right? So let us say that the electric field were not perpendicular to the equipotential surfaces. Okay, let us say that the equipotential surfaces were like, so let's say this was the equipotential surface and the electric field were like this. Okay, the issue is Now this electric field can be split into a perpendicular component and a horizontal component, right? The perpendicular component is fine, but the horizontal component will drive this charge Q to have a motion along this path, right? But you know that these two points have the same potential. So why? That is clearly not allowed, because if it has the same potential, it's not going to want to move there, right? Therefore, the electric field can have no component which is tangential to the equipotential. So when you have an equipotential like that, the electric field cannot have any tangential component. So you must make it more and more normal, and the case where there is no tangential component is the perfectly normal case, right? Only then will the charge never feel any tendency to move here or here. No tendency. That is why the statement is true. I hope you understand that. So you can see in this case, in the case of flat planes of charge, the electric fields are like this, perpendicular. Sorry, in other words, to put it better, let's say there is some charge distribution. Okay, let's not worry about what charge distribution that is causing a uniform electric field. Okay. So by the way, I just want to use this moment to discuss a little bit about uniform and constant. A lot of JEE students have this doubt. Do you know what the difference is between a uniform field and a constant field? Because these two terms occur very often in competitive exams, and people might get confused. Uniform means the same in space. That is, it is the same in space. That is, there is no difference between the electric field here and the electric field here. Okay, they all point in the same direction and have the same magnitude. That's what it means. That is what uniform means. Constant means same in time. So whatever it may have very different spatial things, but whatever it is, it remains like that forever. That's what constant means. Whereas uniform means that is the same always. Of course, this need not be constant. Next moment it could be like that, but it would still be a uniform field. Okay, so that is an important distinction to be made. Okay, so various equipotential surfaces are interesting to draw, right? It's pretty intuitive to find out actually. Just look at the electric field lines. Look at this positive charge. It's going to want to have electric field lines like that. But you know that this charge also has the ambition to do that, right? So when when these two charges both are placed here as sources, this charge sort of bends upwards, has its field upwards, and so does this charge, and like that, right? They both try to interact like that, and therefore their electric fields look like that, both of them superimposed. So you know that the equipotentials have to be perpendicular, right? So you start drawing circles like that. I hope you understand how to draw equipotentials very quickly. So drawing them is very easy. Just look at the electric field lines. You know that electric field lines travel like this, like this. The negative charge wants to pull in electric field lines, right? It wants to pull lines. Whereas the positive charge wants to push out lines. The electric field is away from our charge and is inside. So this negative charge wants to pull, but this wants to push. So this line sort of bends and comes here. So I hope it's intuitive to understand how to draw electric field lines. Once you draw the field lines, just look at all the circles or all the surfaces that are perpendicular to every one of these lines, and that is simply your equipotential. Okay. So I think so far we have discussed that integral E dot dl, right? Negative is equal to the potential, right? And this is, by the way, minus infinity to r. Minus infinity is simply the reference. Why is there a negative sign here? That is because the potential is a measure of how much work the external observer has put in, right? So this is actually technically potential energy. So per unit charge, right? In other words, external force per unit charge. But the external force is actually equal to the negative of the electric field, right? Because you want to just barely exert the enough. You want to barely exert enough. You want to exert just enough force so as to not induce more kinetic energy into the charge. So therefore, you get a negative sign from here. Okay. All right. So there you go. So that is that. And I think you can differentiate both sides. See, this is a slightly more first principles derivation, but I think you guys are. I think you can understand what I'm doing here. Look at this equation and differentiate both sides with R. Okay, dV by dr, right? And I think, do you know how to differentiate an integral? This simply happens to be E of R. So that's it. Oh, so it's negative sign, right? Negative sign. That's it. That is where you get the relationship. The electric field at any point in R is the negative derivative of the potential with respect to R. Okay. Later you will come to know that in 3 dimensions, this is replaced by something called a partial derivative and something called a gradient operator. But we are going to ignore that right now. For all that matters now is that the electric field is the derivative of the potential with respect to with respect to R with a negative sign. Do not forget the negative sign. Very important. In fact, I'll write this equation once again, and you can see you can immediately look at the equation and make a few deductions from it. This is telling you that if E is negative, then dV by dr is positive, right? That means if the electric field is negative, that is pointed in this direction, then actually potential is increasing with R. Do you see that? Potential is increasing with R. So if potential were to be 2 volts here, it's going to be some 5 volts here. It's increasing, right? And this makes sense if you think about it. The reason the electric field is here is because it's going to decrease the 5 volts to 2 volts, right? It's going to, whatever charge you keep here, the electric field is going to take it from 5 volts to the 2 volts. That is why this potential is the 5 volts, right? So you can use that to tell yourself, to convince yourself that this equation is actually correct. Makes sense, right? So there you go. This is a very, very important point. Electric field is the direction in which the potential decreases the steepest. I think we've done this already in the previous one. So let me repeat that point a little slower. The electric field is in the direction in which the potential decreases the steepest. So here we saw that the electric field is always perpendicular to the equipotential, right? So take a look at this equipotential and another equipotential like this. Okay, I'm going to use red for electric fields. So there you have. So you have this equipotential. Let's say its potential is some 5 volts, and let's say this equipotential is going to have a potential of less than 5 volts, right? Say 2 volts. Okay, and why does it have less potential than this one? Well, that is because it is away from the charge, right? It is in the direction of the electric field. So the electric field pushes the whatever charge you have here, and in doing so, it increases its kinetic energy and decreases its potential energy. And because of that, the potential decreases. I hope that's clear. So if this is a 5 volts equipotential and this is a 2 volts equipotential, the electric field, what would be a way of descending the potential? What do I mean by descending the potential is, what I mean by saying, when I say descending the potential, is that you could go from here to here, right? You could travel a path like this. That would also mean that you're decreasing 3 volts. From 5 volts, you're going to 2 volts. right? But this takes a long path. In fact, this takes a longer path, right? You're taking a long time to get from 5 words to 2 words. This is a shorter path. This is a shorter path. This is the shortest path. Directly perpendicular is the shortest path where you can go from 5 words to 2 words, right? The radial path. And it just so happens, it's not a coincidence, but it so happens that the electric field is along this path. The electric field is along the steepest path of descent, of potential descent. Okay. So I hope you see that point very clearly. The electric field could have been like this, but we know that the electric field should not have a tangential component, right? Otherwise, it would push this charge this way. In addition to pushing the charge forward, it would also push this charge tangentially, and that would mean that it would violate the very idea of what an equipotential is. That is, think of an equipotential as a place full of equal energies. Think of like a place of a classroom full of people who have the same potential. So there is no competition, right? There's no everybody knows that everybody is capable of the same thing. So there is no hard feelings. There is no there's no jealousy and so on, because everybody has the same gifts. Everybody has the same talent, same potential, and so on. It is similar in this case. On the circle, everybody is talented the same way. All the points are equipped with the same amount of energy. So there's no way that a charge would get pushed around from one thing to another. Every point here, the charge has the same amount of energy, so it has no tendency to move to another point. That is, in a class of 20 equipotential students, there is no reason why a student would say, I would prefer to I would prefer to give up, and another student would prefer to do it better. I mean, I understand that in the real world it would be very different, but in an ideal world where everybody has equal potential and equal mindset, why would somebody act differently, right? It is the same idea. So, but people would definitely want to go from a higher potential to a lower potential and expend their potential in terms of actual returns, right? So that is what actually is happening. So the electric field is going in the direction of the steepest descent, which is perpendicular. Okay, I think now we come to the potential energy of a system of charges. So by the way, a potential energy is 1 by 4 pi epsilon naught Q1 Q2 by R. I think that is fairly obvious only, because we started out defining the potential as what is the potential energy per charge, right? This is how we define potential. So it makes sense that U itself is Q1 Q2 by 4 pi epsilon naught R R12, where R12 is the distance between them. Remember that there is no vector here. Potential energy is also a scalar. By the way, if you're very interested in what a scalar is, a scalar is a quantity, a physical quantity, which has only one index. Actually, I won't go into what that is. So anyway, the point is, it doesn't depend on direction, right? Yeah. Okay. So an important fact to look at here is that potential is commutative. That is, the potential energy of Q1 and Q2 is the same as the potential energy of Q2 and Q1, because multiplication is commutative. And that should make sense, because it would be very, very unsettling if I just change this Q1 to Q2 and this Q2 to Q1, if the potential were to be different, right? Luckily, it's the same. So now we look at what the potential energy of distribution of charges. So, we have seen that the potentials can simply be added to create the net potential here. So here the potential energy simply multiply the charge here, right? So multiply Q3 to everything and you get your answer. However, there is a very common misconception here. So some people look at this formula, equation 2.25, and some people look at equation 2.26 and wonder, wait, why are they different? Why is there this extra term of uh, Q1, Q2? Why is this extra term there? Right? So remember, this is also potential energy, by the way, and this is also potential energy. So what is the deal here? Why does this have only two terms? Why does this have three terms? Well, the important distinction is what is the question asking for, right? What is the question asking for? That's very important. In this case, in the first case, the question is saying these two charges have already been assembled. Okay. Now they're asking what is the extra energy by bringing the third charge. Okay. For that question, the answer is this one. However, if you're asked how much work done or how much energy is required to assemble all of these charges, then you need to assemble this and this also, even though they're the source charges. That is, you have to bring the sources from some infinite distance away. In doing that itself, for doing that itself, you need some work, right? You need some energy. So that extra energy, so this energy is needed for assembling the sources, because the sources themselves are going to repel each other, right? They are both positive charges, so they're going to repel each other with a magnitude of 4 with this much potential energy, right? So that is the thing. Okay, potential energy in an external field. So now we look at the potential energy of a single charge given a electric field. I think we have already seen that if there is some electric field somewhere, right? You take this charge from from infinity, right? You bring a charge from plus infinity or minus infinity, it doesn't matter, and you bring it to some distance r, some known distance r. Then the potential energy of the charge is q times the potential of the charge. Okay, and this is the work done by the external person against the electric field. Okay, so I hope all of these concepts are very clear. This is the work done by external agent. Maybe you, right? You're expending a lot of energy. You just ate. Why do you eat, by the way? It's a very interesting question. Why do you eat? A lot of people, in fact, this is also applicable in finance. A lot of people want money, right? But actually, what I think is, you don't want money. Think about it. You actually want to spend money. So this is the ultimate desire, because you want to become happy, right? So the want money is only a consequence. So it's only the consequence of this want. So just like potential energy, I'm just relating it to physics. So if you're ever wondering why does a charge go from plus 10 volts to plus 5 volts, plus 10 volts is richer. Okay, plus 5 volts is poorer. If you think about it, nobody wants to become rich just for being rich. There's no use in just having a few billion rupees or whatever and just keeping it in your bank account, right? After having all that money, after having all the 10 volts, you need to somehow spend it, right? Only then that'll make you happy. So you need to make the 10 volts 5 volts. I hope you understand now. That is why everything wants to become poor. There is no point in having money if you don't spend it, right? So that is why charges also, they like to spend their potential. So they have their potential of 10 volts. They urgently feel the need to go to 5 volts and have kinetic energy. Kinetic energy is happiness. Okay. So they want to have kinetic energy. So that is why they want potential. So your want to earn money is your want to get this 10 volts. So somebody has to bring you to 10 volts, right? Once you're brought to 10 volts, you're very rich now. Now you need to spend money. Now you need to get to 5 volts and get a lot of kinetic energy. That's what's happening. Okay. Anyway, So I suppose this is fairly obvious. Again, this is not much in addition. This contribution comes from the external field. And this thing should be vaguely familiar. It's the potential energy of the charges themselves. The charges interact themselves and they have a repelling potential energy themselves, right? And this external field causes this another potential. So you just add them because they are scalars. It is the same for this as well, right? So if you want to assemble the configuration, then this is what you're going to do. Okay, so far we have looked at what the electric field is due to a dipole. Actually, I think we have looked at what the potential of a dipole is only. I think electric field has been covered in the last chapter, so I'm not going to cover it again. But we have looked over the fact that the potential drops off as 1 over r squared in the case of a dipole. Okay, these are very important facts to keep in mind. Even if the exact formula doesn't come to recollection, it is very important to understand what is the dependence of the various factors in electrostatics versus the radial distance or any sort of distance, appropriate distance. Okay, so now we look at something called the potential energy of a dipole. So we have looked at the potential energy due to a dipole. So you see the difference from the previous chapter. We have already seen the potential energy caused due to a dipole. That is when a dipole is here and a separation of 2A. What is the potential here? But now you're asking a very different question. This is not the question. The question is, given an external electric field and you have a dipole like this, now what happens to the dipole? What is the energy of the dipole? So that is these two are very different questions. So let us first consider, I think in this time we will, in 12th grade, we will only consider uniform electric fields. You will find that if you come to non-uniform electric fields, you come to very complicated expressions. Okay. And all of this is not really required. Okay. So anyway, so we will ignore all of that. What you just saw, please ignore. In a uniform electric field, this becomes relatively much simpler. Okay. All right. So let us say you have a uniform electric field. Again, what we've just discovered what uniform means. Uniform means it is the same in space. Yeah. It can change with time, but luckily we know that electrostatics means that all the charges are stationary. The source charges are all stationary. Therefore, all the electric fields are stationary. Okay. So that's important. All right. So let's say we have an electric field like this pointing towards the right. You see all the arrows. They represent the direction of the electric field. And you have a dipole, a plus q and a minus q at an angle of theta with respect to the electric field. We have already seen that this distance is 2a, right? Just as a convention, because you like to call this a and you like to call this a as well. So the projection of this length along the electric field is a cos theta, simple trigonometry. So the torque, so how would you measure the torque? So you have a force here, right? You know the force is q times electric field. We have seen this in the direction of the electric field. So the force is this way. And what about the force here? Yeah, well, the force is still along this way because the electric field is along this way. But the force is minus q times E because the charge is minus q. But a force of minus QE along this way is the same as a force of plus QE along this way. So we prefer to just rename the force as QE but along the opposite direction. So the force is QE along this direction and a QE along this direction. So the torque at the origin, in fact, we later come to see that the torque is actually the same around at any point, but we will right now only consider the torque on the origin. Okay, it's simpler to derive. Clearly, the torque is R cross F. Okay, from the definition of the torque, tau equals R cross F. So in other words, you can just look at the projection. So this is A sine theta, right? So the cross product will simply be QE times A sine theta. So R times F times sine theta, and in the direction of the rotation. So the direction of tau, which is the torque, will be in the direction of the rotation, which is inwards, because the dipole is going to rotate like this because it has a charge this way and this way. Try to, whenever I draw diagrams like this, or whenever you draw it yourself, try to imagine in your mind you actually having something like this, and you're trying to pull this way, and think about how it's going to rotate. It's going to rotate like this, right? So due to the right hand thumb rule, you would say that it's pointing inwards. This is a symbol for inwards if you didn't know. X means inwards, dot means outwards. I'll just write inwards now. So anyway, so QE times A sine theta plus QE times A sine theta is a torque. So it's QE times 2A QE times 2A sine theta. But QE is the force. QE, but you can rearrange this as Q times 2A times E times sine theta. But Q times 2A is a very nice quantity called the dipole moment. That is why we have defined dipole moment as Q times 2A times E times sine theta inwards. And this just so happens to be very beautifully P cross E. Okay. So that is how you come to this formula. By the way, in physics textbooks, people are very lazy to write tau with an arrow on top. So they just bold the tau. These two are the same thing. Okay. So if you ever see a bold tau or a bold P, these are all vectors. Obviously, when we write, we can't sit and make things in bold and things. It will waste a lot of time. So we'll just put an arrow on top. Okay. So there you go. So the torque obviously is rotational analog of the force, right? So it is trying to rotate this dipole, and due to its rotational intention, it is going to create a potential energy, right? The torque is going to want to minimize the potential energy. As we have all seen throughout this while, physics is just about understanding how forces work and how the forces change energies and how these energies influence each other. So in this case, all forces try to reduce the potential energy of the system, right? Because it wants to convert it to kinetic energy. We have just seen that using the money example, right? In the money example, all the forces in the world, that is your brain, is trying to get you to spend the money appropriately so that you can have fun. So that fun is the kinetic energy. Your brain is the force or the torque in this case, and your potential energy is your money or your ability to spend. So that is it. So okay. So now you can see that you can work done in the rotational analog is simply integral tau d theta, right? Instead of writing integral f dx, we can write tau d theta. That is the rotational analog of work. So if you move this dipole from theta naught to theta 1, then your answer simply, it's a simple integration only. P e sine theta d theta from theta naught to theta 1, which is simply Pe cos of theta naught minus cos theta 1. So we define the potential energy at a point. So now again, I told you, right? Every time we need to define some sort of potential, we need a reference. Otherwise, it makes no sense. We can always add a random number alpha and everything would remain the same in the universe. It's all relative. So in this case, we just randomly assume, for a good reason, that theta naught is pi by 2, so that we can make cos theta naught a very nice 0. So we say that whenever the dipole is like this and the electric field is like this, the energy is 0. Okay. This is a random reference level. Okay. It's very nice and symmetric. So I suppose you could use that to justify why this is the case. But at the end of the day, it's an arbitrary human choice. It could be 5. Then you'd have to sit and deal with some nasty, stupid numbers at the end. So why not very neatly define it to be 0? So once that is defined as 0, cos theta naught is 0. So the work becomes minus PE cos theta 1. And that is all the potential energy is. The potential energy U of theta, it's a function of theta because as theta changes, the potential energy changes, is PE cos theta, or in other words, minus P dot E. By the way, sorry, I'm extremely sorry. This is it has a negative sign because torque is the torque applied by the electric field. But the potential or the work done is the external work done. That is what is the work that you are doing to give the particle give the dipole its energy. So this has a negative sign, this is a negative sign, this is a negative sign. So this has a positive sign. Okay. So PE cos theta is minus P dot E. That is the potential energy. So just to recap, torque is P cross E and potential energy is minus P dot E. Please note that there is no arrow over the potential energy because potential energy is a scalar. Okay, so this is all it is, and then this is simply this is the extra term. So if you're again wondering why these two terms might make sense because it is just exactly what you have just derived, right? This term is the same as this term, but then why do you think this extra term is there? That is simply because you're also in this case you're taking into account the assembly of the dipole itself. The energy required to assemble the dipole is being taken into consideration here. Okay. So that's it. So this is the total potential energy of assembling an entire dipole. But in most cases, we just ignore this term because we assume that the dipole is already made. Okay. So technically, you would only consider the potential energy as a function of theta to be minus P dot E. Okay, so we'll stop here. We'll continue in part 2, where we'll start discussing the electrostatics of conductors. We'll look at what a conductor is, we'll look at what capacitors are, and so on. I hope you understood about the potential part. So we are basically done with the potential. In the next session, we'll continue with the electrostatics of conductors. Thank you.